Welcome to the deep dive. We take brilliant sources, unpack them, and give you the insights you need. Today, we are diving deep into, well, the amazing world of our Buckminster Fuller. Imagine, if you will, a building, but it's not just a static pile of bricks, resisting gravity. Think of it more like a tuned instrument. Cables pulling in tension, struts pushing in compression, the whole thing sort of humming right at the edge of motion. Fuller, he was the visionary who really taught designers to see structure differently, not as rigid stuff, but as frozen flow.
That's a great way to put it.
So our mission here is to unpack Fuller's ideas, which were pretty radical for his time, and honestly still are. Things like doing more with less, his whole spaceship Earth concept. We're going to explore how his thinking on structure, geometry, efficiency, how it's all incredibly relevant right now, especially for you. And we'll use motion theory as our lens.
Exactly.
Yeah.
Motion theory gives us a framework, a way to maybe formalize some of the things Fuller seemed to grasp intuitively. So let's just quickly set the stage with MT. At its core, motion theory says reality is fundamentally structured motion. Things synchronizing under constraints.
Like a dance.
Kind of, yeah. A very complex, choreographed dance where everything moves together, but only if it follows certain rules, certain alignments, what we feel as forces. Well, MT sees those as gradients of sync pressure, like the pressure to stay aligned in that dance.
Okay.
And mass, that's like the inertia of rhythm. An object resists change because its internal rhythms are, stable, locked in.
Takes effort to change the rhythm.
Exactly.
Huh?
So good design, in this view, achieves high coherence per resource. More order, more stability, less effort. That's our guide today.
That connects the dots instantly. Okay, so designing with forces, not just against them. Let's get into the man himself. Fuller's journey, it's quite something. He was a dropout, actually. Had some pretty spectacular failures early on with his Dymaction projects. The car, the house.
That Dymaction car looked wild.
Didn't it? 3 wheels, super aerodynamic.
Yeah.
But, it didn't quite take off commercially. Despite those setbacks, though, he was just relentless, always innovating. He's the one who gave us terms like ephemeralization.
Which basically means...
Doing more with less.
Yeah.
Getting the most out of the least material. And, of course, spaceship Earth. That image is so powerful, right? Our planet as this closed system, we need to steward carefully.
Yeah, it really shifts your perspective.
And his interests were just, wow, all over the map. Architecture, sure, but also naval bulkheads, that amazing Dymaction map showing the world flat without distortion, teaching, and his huge work, Synergetics.
Ah, Synergetics.
Yeah, it wasn't just a side thing. It was his whole framework for understanding the universe.
Yeah.
Energetic, synergistic.
And that's a fantastic bridge to motion theory, actually. Fuller's Synergetics. He really insisted that you can't predict how a whole system behaves just by looking at its parts in isolation.
The whole is greater than the sum of its parts.
Pretty much. And motion theory agrees, but it adds, let's say, a way to measure it. Coherence. Where Fuller talked about synergy, MT gives us variables, like alignment, we call it phi, how well things move together. Then there's ordering pressure, S, the drive towards that coherence. And resistance, R, what pushes back against it.
S, R, and phi.
Okay. So Synergetics focus on patterns of forces. It maps really well onto this idea of structured motion. Fuller was all about networks over blocks. Stability coming from distributed alignment, not just brute strength.
Makes sense.
And finding minimal pathways that do more with less. In MT terms, it's about maximizing that S over R ratio, SR, getting more synchronization for every unit of resistance, designing things that are naturally efficient, tuned.
That SR ratio feels like a really useful concept. Okay, let's talk tensegrity. This is where it gets really elegant. That frozen flow idea feels strongest here. Walk us through it. Continuous tension, discontinuous compression. What's going on?
Right, tensegrity. It's fascinating stuff. The basic idea is you have this network, usually cables, that's under continuous tension. They're always pulling.
Okay.
But the compression parts, the struts, the rigid bits, they're discontinuous. They don't actually touch each other. They float, held in place by that web of tension.
Floating struts. How does that even work?
Well, we definitely need to give credit to Kenneth Snelson here. He pioneered the classic tensegrity sculptures. Fuller then took the idea, generalized it, really pushed it out there.
So if the rigid parts aren't touching, how does it stand up? I mean, how does it resist forces? It sounds fragile.
It seems counterintuitive, doesn't it? But from a motion theory perspective, that pre-stress, the built-in tension is like pre-synchronization.
Pre-synchronization.
Yeah, you pay an alignment cost up front, you tune the instrument before playing, This lets the whole structure absorb small shocks, little nudges, elastically.
Mm-hmm.
It can respond without falling apart.
So it's already alert.
Exactly. And it has this sort of distributed intelligence. Loads don't pile up on one weak spot. They spread out through the whole tension network. No single point of failure.
That sounds really resilient.
It is, and
Yeah.
it's scale-free. Biology uses this principle. Your own cells, the cytoskeleton inside them. It works like a tensegrity structure. Pre-stressed networks of proteins.
Wow.
Seriously. Nature kind of figured it out ages ago. MT sees this as life-maintaining coherence by tuning its internal tension to handle local shocks without the whole system going haywire.
Mind blown. Okay.
And that explains why they're so strong for their weight. It formalizes ephemeralization. The pre-stress boosts S, the ordering pressure.
Yeah.
The discontinuous struts lower R, the resistance, the friction. So that SR ratio ordered behavior per resource, it just goes way up. More stability, less stuff, maximum efficiency.
That's a really clear explanation. Okay, another icon. Geodesic domes. Fuller's signature structure, almost. We've all seen them. Huge spans, seemingly lightweight. They distribute loads along these short, triangulated paths on a sphere, right? Giving them amazing stiffness to mass, fast assembly. They look incredible. But what's the physics making them so efficient?
Yeah, the efficiency isn't magic. It's really clever geometry and physics. The key is triangulation. Triangles, unlike squares, don't easily wobble or deform. They lock phase.
Right, triangles are rigid.
Exactly. They force compatible motions. And the structure distributes loads along geodesics, the shortest paths on the sphere. Short paths mean low error.
Less chance for things to get out of sync.
Precisely. Lower phase error, which means higher coherence when forces like wind or snow hit it. The load gets shared quickly and efficiently. Plus, when you subdivide the sphere, like an icosahedron broken into smaller triangles, you increase the modal bandwidth.
Modal bandwidth sounds technical.
It just means the dome can handle a wider range of vibrations or fluctuations without failing. Like an instrument that can play more notes cleanly, it can absorb more different kinds of stress.
Okay, incredible strength to weight. But are they always the best solution? I mean, living in one. Are there downsides? Practical issues?
Oh, absolutely. That's a really important point. Domes aren't a cure-all. They have challenges. Condensation can be an issue sometimes. Cutting in windows and doors isn't always straightforward. Acoustics can be tricky too.
Right. Big echoey space, maybe.
Could be. So they're brilliant, but they're context tools. You use them where they make sense, not everywhere. They solve specific problems incredibly well.
Makes sense. Context is key. All right, let's shift gears a bit from static strength, just standing there, to dynamic change, how things move and adapt. Fuller had these amazing models, didn't he? The vector equilibrium, the VE, and that hypnotic jitterbug transformation. They weren't just toys, right? They showed something deeper.
They really did.
Yeah.
And motion theory gives us a language for that. The vector equilibrium, or VE, with its perfect symmetry. It's like a point of neutral alignment.
Neutral alignment.
Yeah, a state
Okay.
where everything is balanced, low gradient. A tiny nudge can send it smoothly in almost any direction. Maximum potential for change with minimal effort, like a ball perfectly balanced on top of a hill.
Okay, I see that. And the jitterbug. That folding, unfolding thing.
That transformation, watching it move between different symmetric shapes, we can see that as adiabatic rephasing.
Adiabatic, meaning low loss.
Exactly, a smooth, efficient path between different stable states. It shows how a coherent system can change its entire structure without, breaking or losing its fundamental organization.
Right.
How do systems change gracefully? The jitterbug gives us a clue.
And that connects right back to his dimaction thinking, doesn't it? The car, the house, the map. He was always optimizing flows, not just surfaces or looks.
Yeah.
They were motion-first designs, trying to retune the whole system. Even if the products themselves didn't always fly commercially, the thinking behind them did. It shifted things.
Absolutely. And that's core to motion theory, too. Good design isn't just about brute strength. It provides low-resistance corridors for change. It wins by alignment, by efficiency, not by just piling on more material. Fuller got that. MT helps us quantify it with SR.
Okay, so wrapping this up, what are the big takeaways from Fuller? The lasting lessons, and how does motion theory help us, actually use them today?
Well, MT definitely keeps some key Fuller ideas. That distributed pre-tension view of stability from tensegrity.
Right.
That's fundamental. It applies everywhere.
Right.
Ephemeralization, doing more with less, becomes a target we can actually measure. Maximizing coherence per unit mass or power. It's not just a nice idea, it's an engineering goal.
Makes it practical.
And his global systems view, spaceship Earth. That needs feedback loops, smart design, not just isolated fixes. MT embraces that interconnectedness. But Motion theory also revises or refines some things. We see synergetics more as a powerful design language, a source of brilliant insights, rather than a wholesale replacement for physics.
Okay.
If some of the math gets a bit specific or numerological, we can use our S, our phi variables in standard mechanics to test it rigorously. We also make sure people like Kenneth Snelson get their credit for tensegrity. And we ground do more with less in testable metrics. Buckling loads, energy use, assembly time, make it real.
So it's about taking the genius and making it testable, engineerable. Can you give an example, like an experiment Fuller would have loved, but maybe with that MT rigor?
Oh, sure. Imagine building an active tensegrity mast. Maybe a meter tall, sensors, little motors pulling on some tendons, the MT idea. Keep the product of tendon tensions constant, a simple alignment rule. We predict its buckling load increases for the same mass. You could test that, load it till it fails, measure damping with and without the rule.
Okay, that's cool. Real numbers.
Or compare a geodesic dome to a standard frame building. Same mass, same span. Measure how much it deflects, how much wind vibration gets through.
Mm.
MT predicts the dome has lower phase error, recovers faster, more coherent response.
Proving the efficiency.
Exactly.
Right.
We could even build a model cytoskeleton in a tank, apply forces, and see how coherence propagates based on pre-stress. Or create an ephemeralization scorecard for shelters, comparing different designs based on performance per unit of resource, kilograms, energy, person hours. The best design is the most coherent per resource under stress.
That sounds like a really productive way to build on his legacy, give it legs, scientifically. But we should also touch on the critiques, right? No visionary gets away without them.
No, definitely not. And it's
Well,
fair,
very-
the overreach in synergetics, as we mentioned, some parts are less physics, more exploratory geometry. NT keeps the useful insights, drops the numerology if it doesn't hold up to testing.
Mhm.
The attribution thing with Snelson and tensegrity is important for historical accuracy. And the practicality of domes, they're context tools, not universal answers. Condensation, openings, acoustics are real factors.
So acknowledging the limitations while keeping the core wisdom.
Precisely.
So if we boil it down, Fuller was really asking us to stop seeing structures as just dead weight. He wanted us to see them as living things almost. Organisms of motion. Networks that listen, adapt, hold their tune. Design like a dancer, not just a builder.
Exactly. And motion theory gives us the physics for that poetry. Coherence is the goal, the thing to optimize. The SR ratio is the budget, the efficiency measure. And phi, alignment, tells you where stability lies naturally.
So where the 20th century might have said more steel, Fuller's message for us now is really more sync.
Yeah, build like a musician. Tune the system first, achieve that coherence, then let it perform.
Build like a musician. I like that. Okay, here's a final thought for you, the listener, to take away. What if we started looking at all our systems, our work routines, our communities, global infrastructure, even just how we organize our day? What if we saw them not as rigid blocks fighting forces, but as flexible, tunable instruments designed for more sync? How might that change what you build, how you connect, or just how you move through your world?